Okay, so before I continue this part, let me show you this. Okay, so this is actually the distribution, the curve distribution of your midterm, not the makeup one, the original one. So after I think and I see the score, after comparing with the makeup one, and I feel that the original one, you see that it's not really symmetrical for the distribution because too much here. So that's why we need to make up class because it's not, the distribution is not good. So basically, the idea is to make the distribution is more symmetrical in a way for the curve distribution. I cannot tell you like how and why because it will take some statistic courses. But what I want to tell you is actually within this part here. So usually how I grade the score is basically I will take like third region. Okay, so this will be the one who fail. This is the one who are in the average distribution, the biggest one here, and this is the one who gets maybe A or A plus. But here, this is the original one because it's not really fit within the normal curve. So that's why we have a makeup. And I think I forgot to make some additional policy. Okay? So it should be to make the distribution is more clear and also fair for all students. So I think this one here, the region that is already here for the original midterm, at least if they already get 70, if they take the makeup exam, the percentage should be different from the other one who has within this range. Okay? So I should make this as additional policy at the beginning, but I forgot to mention about that. And since like the result of the makeup, some of the scores maybe went up really, really high, and then after some computations, it's also making really, really huge improvement. So it will also change the distribution, so it will not really in a normal curve, fit within this. So I'm adding as additional policy for those who are. So maybe right here. So if original midterm is already greater than 70, the percentage will be 45 original if you take the makeup exam, and then this will be 50% makeup. And the second policy, because I changed some points after you finish the term, then some students getting more than 100. So I need to keep the limit as 100 to make it more fit with the curve. Okay, it's related to the distribution of the curve. Okay, and then the limit is the limit of maximum makeup will be keep at 100. Okay. So I think the way we see is if you already have like at least 70, you still get plus, but not that really high. Okay. So I think it will be very fair, especially for those who are already went up the original, maybe he has already 80, and then he joined again to improve further with the 35 and 65. I think it's not fair, right? So I believe to make it more, the curve fit with the normal curve, I think this should be okay. I checked within this numbers. I checked the statistics. I think it's okay. For the distribution, it's okay. So you still get the improvement, but not that much as the previous percentage. Okay. Okay. So just an additional policy and some percentage. Okay. So I hope everyone can, if you already count or maybe compute your score, you can now using this for the 70, at least for the 70. Okay. Yes. Okay, I hope it's very clear for everyone.
The makeup score, if you get the whole settle,
How do you do that? Yeah, I keep the minutes for one. Sorry about that. Sorry. Okay, if you have any more questions or maybe some suggestions, let me know. If you have maybe other ideas that can help the class or help me to review the class, just let me know. Okay. Okay, now we go back to the integration, the area between curves. So next week, so let me write here. So 12, 5th, this will be no class, okay? No class, but you have 2 hour TA, okay? 2 hour TA. So 2 hour TA. And then for Thursday, we will have a class as usual. I mean, no class means this class. So you can have 2 hour TA starting from 2 p.m. right at the right. I will announce it. So 2 p.m. until the 4:30.
Regarding this verb, I'm passing this. I'm not sure. Like I'm passing very
Yeah, I think this is just from the meter. Of course, it's like really small. That's why it's not really. No, only next week. Only next week. Only one day. Okay. Okay, let's continue. So let's start from here. It's the same. I think it's the same example in your textbook. So if you have the textbook, you can see. Okay, so find the area y equal between the y equal 1/x and y equal x. Okay, and then also y equal 1/4x. So you have 3 terms. You have 3 terms, and you're going to find this area together. Maybe next week quiz. Quiz next week. Are you okay with that? No. Maybe next week. Yes. Yes. Please. Yeah. 5 next week. Yeah. Maybe next week. And then sometime after that, final exam.
So Wednesday, work quiz and then final.
Yes.
Okay.
Yes? Which one is Thursday? 22 or 21? So maybe 5. So 14. Oh, so quiz and then 1 week later final exam. Is that okay?
I told you. Yes, that was
When should we do the final?
that means 31.
For Christmas.
But if you want, I can make it after Christmas. But I don't think it will be.
Very
It will ruin your holiday.
Merry Christmas.
Well,
Yes.
What is the content of
All related to the integration from the fundamental theorem process up until the techniques. Okay. Okay. So let's go back to this picture. So we can have, if we want to take this in area between curves, we can split this, become the here, right? Become this. That's the first way we see. So this will be A1 and A2. So the area is A1 plus A2, which we need to find. Of course, we need to find this point, these 2 points, right? So that we need to find the interval. Of course, if you see the picture, we have 1 and 2 already here. But if it's not given, so we need to find the intersection. Okay? So always find the intersections. So first is finding the intersections from the, so find the intersection. So equaling the 2 curves, so 1 over x and x. So we take that and so it's actually, we get okay, I think we can write that. No. So x is 0 and x is plus minus 1. So we have 1 and we also have the other part with 1 over 4x equaling the 1 over x. So x is 4 over x. And we do the same thing. And you have the I think let me write clearly. Let me write clearly. I think we can just solving this and get the x is plus minus 1, and then so we have x for x, so x squared plus 4 minus 4, sorry. So x is plus minus 2. Okay. So we have 1 and 2. So we can write, first is the area 1 is integration from 0 to 1 x minus 1 over 4x dx. and this is plus 1 to 2 1 over x minus 1 over 4 x, right? And then the x. And compute each one of them. So we can take this, make it become 3 over 4, right? And this one, we can just simply take the integration from 1 over x will be ln, right? So this will be 3 over 8 x squared, and then plug in 0 and 1. And plus, this one is ln x. This will be x squared over 8, plug in 1 and 2. So this will be 3 over 8. And plus, this will be ln 2 minus 4 over 8. And then this is minus 0 and minus 1 over 8. So plus 1 over 8. So negative 3 over 8, it will be 0. So we'll be having ln 2 as the answer. Maybe this is too tight. Let me move here. Okay. Okay, another way to see the calculations is by taking this line here. So we can also check and take this as area 1 and area 2. So we can see from two perspectives. So sometimes there will be some cases where the area between curves you can choose using dy or dx. Sometimes one way may be easier. Sometimes maybe you can, or you can choose which one you prefer. If you prefer like dx, I think you can just using the first one. Or if you want to use dy, then you need to write the function of y. Okay? So for example, for this y equal 1 over 4x, it will be x equal 4y. So 4y is the function. Okay? So we can write here. And this will be half, right? So if we would like to write A1 and A2 for the area, so we write A1 plus A2, and in our case now, it will be integration from 0 to half. And then, remember, it's always top minus bottom, but if we are getting this dy, so you need to rotate a little bit, so this will be your top minus this one, okay? The right minus the left, or top minus bottom. So this will be 4y minus y dy, and plus from half to 1, and this will be 1 over x, so it will be 1 over y minus y dy. Okay, this will be 3y, so 3 over 2y squared from 0 to half, plus this will be ln y minus half y squared from half to 1, and this will be 1 over 4, this will be 3 over 8, plus this will be ln 1 is 0 minus half minus ln half is minus ln 2, right? And then minus 1 over 8. So plus 1 over 8 minus sorry, this will be, so plus 1 over 8, and this will be negative 4 over 8, right? So negative 3 over 8, so 3 over 8 will be cancelled, right? So this will be cancelled, and then we have, this will be ln 2, the same. So again, you can choose using dx or dy. Okay. For some cases, both are okay. Zoom out. Okay. Now I think the more you are able to solve, try to look the exercise and find some questions, and especially for area between curves, whenever you find this type of question, the first thing is you need to identify how the curve is. Right? You can sketch, or you can find the intersections and start from there, and then do the integration. And the integration will be not that complicated integration. Like for example, like this, it's supposed to be not really much calculation, right? So the difficult part is setting up which one that you are going to integrate. Okay? What is the interval? Okay? Okay, I think we can go a little bit. Oh, there is some question here that I think I will just take it, and I think I can upload this into the Moodle. So some examples here, and it's not given any curve that for sure that you need to sketch first. And that's my suggestion. Always sketch the curve. Do not try to directly compute unless you are familiar with it. Sometimes for some function that you know, you can just do directly the calculation. But my suggestion, start from sketching, okay? Especially for a function that is not really that you don't really know. Okay? Maybe try some of it. Maybe from here, maybe one question. There's a lot. And for hyperbolic, I think we can skip the hyperbolic. Okay, skip the hyperbolic function. Okay. Any number that you would like to solve? One number? Any? No? We solve it together. 23?
25.
Oh, 29?
25.
Oh, this is interesting.
25.
25?
Yes.
Maybe 25. 25, we have square root of x. And then we have 1/3x. And we are given interval. So I think should be able. And square root of x, we can draw, right? Or no? Remember, square root of x is actually the result of an inverse of the x squared, right? If you remember, x squared from some part of its domain, you can invert and then make it the square root of x. Right? So basically, if you want to draw really perfect, you can draw the x squared, take the y over x, and then mirror. Okay. What I mean is, you can take this. Or you can just assume. I think it's also okay. I don't really care much on the graph as long as it is proportional and okay. Okay, this is the so think we can just erase everything. Or maybe not erase everything. Okay. Erase only this x squared. And then we have 1 over 3x. So 1 over 3x, it will be maybe I can just rotate a little bit, right? Very minimum energy, very efficient. Maybe here. Suppose that this is 1, 2, 3. This is supposed to be 1. So I think I need to make it more lean up a little bit. Okay, I think this is okay. And then adding that. Okay. But then we have interval 0, 16, so it's quite long. So I think I will just make up and then just make it 16. Okay. So 16 will be, this will be 1, 2, 3, 4. So at y equals 4, it should be 16. So maybe this is x equals 16. Okay. So I think that is the curve. I think we can just take the area as integration from 0 to 16. And then we can take square root of x minus 1 over 3x dx. So half plus 1 is 3 over 2. So x 3 over 2, 2 over 3. And then minus 1 over 3 x squared or 6. Right. And then plug in 0 to 16. And 0 will be 0. So we can compute with 16. Yeah. 16 is 4, 4, 4, 64, 128 over 3. So 16 and 16 is what? 256, right? 256. 256 divided by 6. Is it correct? So 16, 16, 6. Let me check. Okay. Well, it's become 0. Do I have wrong here? I think maybe our graph is wrong, right? So I think this should be, we need to find the intersections, okay, to make it clear. So, right, so that's one that I forgot to check. So x is this. So, maybe this need to be first thing first. So 1 over 9x is x minus 9. So there will be something at x equal 9. So yeah. Oh, so I'm wrong here. Yay. So I need to make this a little bit go there, and then suppose that the 16 is over here, and let's say 9 is here. Oh, of course it's a little bit weird, but let's say that is what happened. And why is this getting lower? Okay, so then our area will be this and that. So this should be 9. This should be 9, and we need to plus 9 to 16. Now it's 1/3 x minus square root of x dx. So let me make erase. Okay, what happened now is we take 1/6 x squared minus 2/3 x 3/2. Okay, this will be what? 27, right? 27 divided by 3, 9, 18. So 18. And this will be 81/6. If we divide by 3, it's 27/2. Right? Plus. Now we have 128/3 minus 128/3. Make it precise. Minus, this will be 27/2 minus 18. Okay. So this will be cancelled, and what will be cancelled again? So 27/2. This is 36. 36/2. Oh, wait. I almost getting wrong. So this will be 9, right? So it should be positive because of this 1. So 9 and another 9. So it will be 9, right?
Yeah.
Yes, okay. Finally.
After lunch is difficult to compute. Okay. So as you can see, if we are not getting the curve correct, we get the wrong conclusion. Like I did. I forgot to find the intersection. Yes?
Can't you just use the triangles? Can't you use triangles?
Triangles?
Yeah.
Which part?
Like, so I did, you integrate like just square root of x, and then you minus with the triangle under it, and then you use the triangle at the top.
The triangle part is okay. Yeah, I think it's okay. I think geometrically, because it's not like a smooth curve, I think it's okay. using triangle. Interesting. But I think there will be some part. I'm not so sure about triangles on this
Oh
side.
yeah, the top.
Yeah, not sure. But for this one, it's I think still. If, for example, you find until 0 to 9, I think still okay. 0 to 9 is still okay. Okay, I think we can move on first, okay? And then maybe we can have exercise more later, okay? So that's the example. You can try the other questions, okay, other functions as well. Okay, now we are moving to the second part of the chapter 6, which is the volumes. Oh, if you want to take notes or take a photo. So, in the integrations, we define that it is the area under the curve. Right? So what happens if we try to find a volume using integration? For example, if we look at some geometrical shape that we can think of, like a cylinder or maybe box, or maybe any cylinder, that basically we say that how to find volume is basically the area multiplied with the height. Right? So if we have the, let's say the functions, maybe just a random function like this. So if we can imagine this line here, and then it's rotating with this x-axis as its center. So imagine this is center, and this will be rotating. And then the rotation itself is creating some shape that if we imagine that the whole thing inside here, or the area under the curve, will be a solid. Okay? So if you could imagine, this will be something like this. Okay? Something like this. For example, this is start from here, okay, so rotate here. So you can have like a solid, and if you slice this up, we will have some area inside. Okay. We can write the area as a function of x. And then if we divide this some sort of slabs, okay, we call this slabs. I will write what is that, is slabs. So if we divide this and cut every part of it with some delta x, okay, the distance is delta x. So we could have something like this, okay. So we could have like, this is actually like a random shape, but we could imagine like it can be any approach to some function. So we could have this, okay, and then we take some sample points for this. It can be any point, but we can take some sample points here, and then we could see like if we have some n, and we can increase the n, right? We can have like 10, 11, 20, and every possible number. We could also did this. Right? Similar to what we have in the area under the curve. So we have the function, and then we have area under that function, and we could say take the rectangle and then cutting all the elements. It's similar. So the more we cut, so the number of n, you'll see that it will getting more smoother and smoother, and it's getting more closer to the volume of the solid itself, right? So using that approach, basically what we say about volume of this is basically, or let me write, approximately will be the area, okay, the base area at some certain sample points, okay, let's say the xi as our sample points, multiply with
the delta x. So this volume is actually volume of one slab. This is volume of one slab. So this is the area, the red one here, and this delta is the height. Okay, that will be the volume. And intuitively, if we add all the volumes for all slabs that we count, like we slice and we add all together. So adding all volume of these slabs, then we get approximately sum we get this approach. And of course, if we keep increasing the n, as n getting infinity, then we are going to take this into our limit definition. And so we can say that volume can be written as limit and suppose that we take from the interval a to b, this will be the volume. Okay, now I will write again this part, okay, this the latest part here, the more clear, I think, this one. So if S is a solid and it's on the interval from x equal a to x equal b, and so on and so forth, and the cross section of S is the A, and then we have this. But still, it's not really practical because we still have this area. What is this area? So we need to define it. So first is we are going to imagine that we have a sphere, okay? Sphere like a ball, right? Let's say sphere with the radius r. So r is a constant, not a variable. So let's say sphere with a constant r. So suppose the sphere has constant r. And then we would like to know the volume of the sphere throughout the concept of the integration. So let's say we have the x and y axis. So everything on the left side will be negative. Also this is also negative, right? So we slice this sphere, and then we see that we have this area, which is actually this area, right? So we see this area, and then we define that this area of the sphere is a circle. Agree or not? Circle, right? So circle, area of circle is what? Pi r squared. Where is the r? Now r is y. Right? This one. Okay. So maybe let's go to take this and right here. So this will be r is equal y, right? But we want all the variable in terms of x. So we have a constant r, we have y here, okay? So we could set some relations between x, y, and r. So x will be, or x squared
plus y squared is r squared, right? Okay. So let me write that. Write that x squared plus y squared is r squared. So if you want to write in terms of y, then this will be square root of r squared minus x squared. The negative part of the square root I will remove because we are focusing on the positive one. So we can write y as this. Okay? And now, based on what we have on the volume from A to B. So let's decide that the sphere will go from this negative r to r. Okay? So let's write that here. We can write the volume is I think we can have a break. Everyone. Okay, everyone. Let's go back to the class and wake up from the dream. Wake up from passing balloon. No, I'm kidding. I'm kidding. Okay, so first thing is why we need this. Okay? Because in my idea here, we are going to treat this sphere as we did in our integration before. So which means that since this r is a constant, so we can just ignore r, this is just a constant, but we want to make sure that this y is in terms of function of x. Okay? So this is a function of x. Okay, so because we have y, this y, then we can compute the area, right? This area using the circle. Okay. Using circle area. So let me write here. So the area is just pi y squared. And y in terms of function of x, we can write that this pi, and then we can write r squared minus x squared. Okay? And we remove the roots basically, right? Because it's squared. So we can write the volume as pi, right? Pi and then r squared minus x squared dx. But since we know that this will be symmetrical, okay, I will state from 0. Okay, I will write again the volume. So it becomes 2 pi, and then we can start from 0 to r, and then r squared minus x squared, and then dx. So do the integration as usual with respect to x, which means this will be x r squared, and this will be x cubed over 3, and then we put 0 to r as our endpoints. So we are going to get, or maybe let me write here, it's 2 pi, and then this will be r cubed minus r cubed over 3. Which is, this will be 2 over 3 multiplied by 2 is 4 over 3 pi r cubed, which is the volume of the sphere, right? Or you didn't remember? So if you don't remember, you can do this. You can do this whole thing integration. This is volume of sphere. So what we did is basically, suppose that we have like this sphere. We can think this sphere we can write down as why? What's happened? Okay. Let's say we have this. If you want to rotate this about x-axis, So we are going to have that shape, right? So if we rotate this, this will become the area if we cut this down. So we are kind of having some kind of like this similar with your sphere. When you cut down and you can like slicing up and you have a circle, right? And this is also the same. You have something like a circle here, which you can approach with its radius, right? So radius will be the function, the height. The height will be the radius. And you can find the area, multiply with delta x, and that will be the volume. Okay, this is what we call the disk method. So right here, this is what we call the disk method. And if it is rotating through the y-axis, then this is the circle. And we have the same approach. We're going to have the circle, the area of the circle here, multiply with the delta y. And that will be another way to see. So this will be this method with the dx, and we can also have for dy. And maybe we are going to have some examples for practices, okay? Yes? Okay, so we call this also or if you see it here first, this is some example on the sphere. We can have many ways to slicing up, but if we increase the number of the slabs or the circle, we are going to see that it is going to approach the exact value that we want to find, the approximate value. Okay. So this is we call the solid of revolution. Okay, solid of revolution. This is if we revolve or rotate a region about a line. It can be axis. Okay. And the key points of the solid of revolution is finding the area. Okay, finding the area. Okay, so if we have let's see, for example, we have example here. This is a y equals square root of x. Okay, so we have y square root of x from 0 to 1, and then rotate about x-axis. So as usual, we start drawing the sketch, and imagine that this will be rotated through here. It's like a bowl, and then you can see that we have this slice here, which has the delta x, and we have the area here. The area, it will be depend on this radius, and what's this radius? Basic radius is y, which is square root of x. Okay. So let me write here that this is going to be y. So the area, we can start taking the area first, pi y squared, or in terms of x will be squared of x and it's squared. So we have pi x as a function of area. So then the volume will be integration from 0 to 1. You can write this first to give you the idea, and then we exchange this to be pi x dx. And then we could just write directly that this will be equal to pi over 2. Okay. Now similarly, this method also works for this one. So suppose that we have y equal x cubed, and then we would like to rotate about this y-axis. And let's say we are going to take the interval from this 0 until y equal 8. Okay, this will be the whole region that we are going to rotate. So we rotate about that, and we have this shape. Okay. So this will be now our radius, right? The radius here, which is in terms of x, now is equal to function of y. So we could write that the area now is area of y. This will be pi, and then x squared, or now is pi is squared or cubic root of y squared. So pi y 2 over 3, like that. And then the volume we're going to get from 0 to 8 of the a y dy. So this will be pi y dy, and integrate, we could plus 1, so it will be let me write pi and then y. It's 5 over 3, so 3 over 5, and plug in 0 to 8. So 8 is, if take the cubic roots, it will be 2. 2 with power of 5 is 32. 32 is 96. So 96 over 5 pi. Okay, now it's very simple, just to show you the simple disk method. So you can look at dx or dy, you can choose, right? And then the next thing is, wait here, oh, this one. So let me write the question first before giving you the context. Let me write maybe here. So find volume of solid obtained by rotating region closed by y equal x squared about line x equal -1. Maybe this will be later. Okay. Maybe we can start with maybe the x-axis first. X-axis first, sorry. And let me write the second question. Also try rotate about x equal 1. Okay, so it's basically 2 questions. So I will move this here. So first is we rotate about x-axis, which I think if we draw clearly, and this is not a complicated function, it's a very simple function, y equal x and y equal x squared. So we have y equal x squared here, y equal x there, and this is the region. Okay, this is the region, and we can find the intersection easily. And we rotate this, and see what we have when we rotate this. If we rotate, can you see something like this? Very difficult, right? Very difficult to imagine. But we don't really care much about what the shape will be. What we care is this circle, the circular shape. This is what we care. So as long as we can make this circle, we are able to find the volume. Okay. So how to imagine the circle? So the circle, because we have something that is missing in between, so the circle will have a hole. It's not a full circle. Okay, it's not a full circle. So the circle will be like this, or we can see from the top, this is the area that we want to find. So there will be some hole that we need to define in our calculation. So we are going to have the outer circle minus the inner circle. That will be the area. Okay? If you want to imagine like how this should be or how does it looks like, it's like when you wash your hand. In the bathroom. Similar shape, right? It can be like that. This is the sink.
Like going down the drain.
Yes. Right. Okay. So this is also we call the washer. Okay. This is we call the washer method. So the washer method. Okay. Like a washer when you wash your hands. Okay, so how we deal with this? Basically taking the area and then taking the, so we need to see which one is the outer. So the outer one will be the x, and the inner circle will be the x squared. Okay? So this will be the x, this will be the x squared. Okay? So let's write in there our equations. So this will be x squared and then minus pi x squared and then squared. So we have pi x squared minus x to the power of 4. So the volume is then from 0 to 1, we find the intersection easily, and then we put in x squared minus x with power of 4, and then the x. And then this will be pi, multiply with integrate, and plug in 0 and 1. So basically 1 over 3 minus 1 over 5. 5 minus 3 is 2. So 2 over 15 pi. So let me copy this. I will make another illustration from this part. Let me crop this. Maybe let me crop again to make it clear. Okay, that's the volume. So now the second question is if we rotate this through the x equal 1 or x equal, maybe not equal 1, sorry. Let me revise this question to make it more beautiful graph. Let's take x equal negative 1. So let's say our 1 is here, maybe negative 1 is here. So let me write And then we have, this is 1. This is -1. This is x equal -1. So now, imagine this part rotate through the x equal -1. Okay? So it will be the same as we did in the previous one, but it's now in terms of dy. Okay, and it's same circle with a hole, right? Circle with a hole. So we imagine that this will be, let's say this is dy, and we could write this as x equal square root of y, right? And how we decide the area? How the outer radius? Remember, usually we rotate with x-axis or y-axis. If we rotate through this, then we have some additional, how many points here? Additional one. Right? The distance here is 1. So the radius is just adding the radius from here, adding 1. Okay? So the outer radius, pi square root of y plus 1 squared minus pi. Now is the other one, it's just y, and then plus 1 squared. Oh, sorry. Okay. Okay. If I have until this part, and this is the circle, then you agree that this is the outer radius, is the square root of y, the inner radius is y. Now we move the center. The center moves to x equals -1, which we have additional distance, right? So this one go through here. So we have 1 plus the radius, right? The whole radius here, okay? So square root of y plus 1, okay? Y is keeping on and off. Oh. So this will be the radius. Okay. So this is 1. So it needs to, so if we want to look at the outer radius, then this plus this, the inner radius from here, from x. Okay. So then you can use this area to find the volume. So it will be from 0 to 1. I will write pi outside, and this will be okay. I think I will leave this to you for calculation. So this will be y plus 2 squared of y plus 1. Okay. Yang mana dulu? Karena sini. Ini. Kalau dari sini.
Oh, tetap soalnya juga ada di sini.
Iya.
Bukan pakai ada. Kalau sekarang gimana?
Semuanya diganti jadi fungsi.
Oh, itu doang. Tapi sama itu sama.
Sama. Okay, any questions? We haven't yet tried some practice from here. It is just all simple example. And it is all the simple example. Supposed to be like introductory questions. Okay, maybe later we are going to have some practice on this part. Okay, any questions? Now think about this. So we have this method. We have the washer, which has the hole in the circle. And let me just give you some introductory questions. So let's say, suppose region R is enclosed by what is the solid if R rotated about x-axis? Okay, so we have 2x squared minus x cubed. And if you think like how to sketch a curve, we already did that in calculus part derivative for sketching a curve. So I hope you are still remember how to sketch a curve. If you are like now, okay, sketch the curve and you still x equal 1, y equal and you did the table. You already have the calculus part on that, right? So use the first derivative, second derivative, find the increasing function, decreasing function, concavity, all the things. So it's also applicable. It's also applicable. So this from here, for this one, we could make like, it's easy to derive, right? We can derive the first derivative, become 4x minus 3x squared. And we find the critical point, right? And also we find the second derivative and the concavity. Just to refresh, let me write. At least this is the core, like the principle. When you are asked, like, what is the sketching curve in calculus? It means like you know first derivative application, you know the second derivative application. Basically this. The other part, like the asymptote, the intercept, the domain, and everything, they are additional. But the core principle in the calculus for sketching curve is understanding the visuals of first derivative and second derivative. At least that. If you have this, then I think I just could give you the, so it's increased from, or let me write here. So for x minus 3x squared equals 0. So x is 4 minus 3x. So x is 0. And x is, or x is 4/3, right? So you could have that so equaling 1 is positive. And equaling 2 will be what? Will be negative, right? Negative. Negative 1 will be also negative. So decreasing, increasing, decreasing. And then the second derivative. And we check this 2/3. Of course, this will be positive, and this will be a negative, right? So concave upwards, concave downwards. So we have, this is 1, 2, maybe 2/3 is about here. And then 4/3 will be around here, or maybe a little bit closer to this. Oh, sorry. So that will be concave upwards and then downwards, downwards, and then the maximum here will be that, and then that. Okay. Now the question is asking the if rotate here. So we know everything now. How to rotate this? Boundary is y equals 0 and this. How to find the volume? If we slice this and similarly we have the dx, it seems that we rotate with what? I think we still can try, right? This one, right? Okay. If we rotate through this one, if we rotate through y-axis, so if we rotate through x-axis, we can, right? We can have like a, how do you say that? I know in Taiwan there's one traditional, like, and then it's rotating. What's that called? Yeah, I think so. Right? It's similar, right? And this is the rotation. Okay. So if we rotate now y-axis, what's happened? So we take this, okay? Okay. Now the problem is the green one's problem. How do we make this, and what will be the radius? What will be the radius? Radius is supposed to be like the outer minus the inner one. But the radius itself is this function. The inner one is function. So it doesn't really work well, right? So we need to think how to get this and how to compute the volume. So we are going to use another method. So we have the disc, we have the washer, and this is what we call, later we call the cylindrical shell. Cylindrical shell. So suppose that we have rotate this, okay? Rotate this, and I will take some part of it, like a really small, and then rotate. And imagine that there will be some kind of cylinder. Okay, so we have a cylinder. Okay. Now the cylinder will be, let me complete the cylinder. And suppose that we have the inner radius for the cylinder. The name is R1. And the outer one is R2. So the total volume for the cylinder, okay? So volume of cylinder. So the inside is hollow, okay? Like a can. Okay? When you open a soda, it's like that. So volume is V2 minus V1. Okay. So this will be pi R2 squared, and let's say we have the height. This is h. So let's write this h and minus. Okay. And then this will be pi h. We can factorize. Okay. And suppose that we are going to factor the r. Okay. So we are having volume pH R2 plus R1, R1 plus minus, sorry. Okay. Now let's assume that we have some distance over here, this one here, that we call, this is R2 minus R1, which is the delta R. So delta R is R2 minus R1, and R is the average radius, or in our case R2 plus R1 divided by 2. So suppose that the R is this one. Okay. So it's in between R1 and R2. Okay. Suppose that this is the average radius. So then we can exchange everything. So this will be 2R. This will be delta R. Okay. So volume is 2 pi R H delta R. This is the height. The delta R is the thickness. And 2 pi R is what? The circumference, right, of the circle. Okay. We could think also using the fact that 2 pi r h is a surface area, right? The surface. Or you can slice this up. You can slice this and then stretch the whole thing. So you could imagine that if we take that, we can have a rectangle. Okay. So if we, let's say we have this, so if this is going to be in terms of x and y, so if the radius is, the average radius is x, and we have, this is f of x, and the width is the delta x. So we could translate this, and taking this is delta x. The whole thing here is 2 pi x, right? And this is f of x. So we could break down and cut this open. And basically 2 pi r multiplied by h is the surface. Or we could say that 2 pi r is the b circumference, right? The circumference of the circle, this circle here. And this is what we call the cylindrical shell method. Which we are going to get through next Thursday. I think we can finish up on this. Finally. But you still have PA. So sad. Okay, I will continue next Thursday to finish off with the formula in application in integral. Like this one, if you rotate to y-axis, I don't think this method will work. So cylindrical shell actually work for every kind of condition actually. But sometimes it will take some time to write. But this method, however, if you could find it, I think it will be very direct. It will be very simple approach. But if you cannot find, then the only way is simple. Okay. So that's it.